Hi, this is a presentation on FetchAid, making parcel lockers more accessible to blind and low vision people with deep learning enhanced touchscreen guidance, error recovery mechanism, and AR-based search support. With the growth of the e-commerce industry and parcel volume, parcel lockers have become an increasingly popular means for package drop-off and pickup in the logistics pipeline. In urban environments, couriers drop off packages in parcel lockers and recipients fetch their packages from parcel lockers. Parcel lockers are widely adopted in different countries, such as Amazon Locker in the US, DHL Pack Station in Germany, and Hivebox in China. Parcel lockers consist of a large grid of compartments where the package is stored, and a touchscreen for interaction. Typically, users select to fetch package on the touchscreen, scan the QR code or input a number code, open the door that contains their parcel, and fetch it. Research has shown that this task is highly visually demanding and thus inaccessible to people with visual impairments, especially in three parts: the touchscreen interaction, target open door detection, and safe navigation to the target. As a result, making package fetching from parcel lockers accessible to people with visual impairments calls for an integrated solution to overcome these three main challenges together. We present FetchAid, a mobile application system that provides real-time guidance and feedback to help PVI pick up packages from parcel lockers. FetchAid helps PVI in two phases: the touchscreen interaction phase and the open door searching phase. In the touchscreen interaction phase, the user interface on the parcel locker poses unique challenges. The interface is usually filled with distracting factors, such as advertisements and other buttons like deposit package, so people with visual impairments could easily enter wrong pages. Moreover, with no screen reader or braille available, it is difficult for PVI to know if they have tapped the correct button or input the correct access information, thus causing potential errors during the interaction flow. So we have derived 4 design considerations for this phase, according to the prior work and our investigation with parcel lockers. First, our system should guide BLV people to the target button on the parcel locker touchscreen. Second, it should offer real-time feedback on the interface operation status. Third, it should implement an error recovery guide for irrelevant page entries in FetchAid. Finally, FetchAid should enable streamlined QR code scanning for automatic compartment door opening in the later phase, rather than requiring users to input a numeric pickup code. FetchAid in this phase tracks the user's finger relative to the fetch package button and uses voice feedback to actively guide the user to tap the desired button. And if an error is made, detected by the page tracking model, FetchAid has an error recovery mechanism that guides the user back to the previous page to start over. Once the correct button is tapped, FetchAid automatically scans the QR code and unlocks the compartment door, circumventing the need for user input. Here, the user is on the home page. FetchAid guides the user to tap the fetch package button.
向左下移动，向左下缓慢移动，向下缓慢移动，向下缓慢移动，向下缓慢移动，请点击触摸屏取快递。
When the user taps the Fetch Package button correctly, the QR code page will show up on the touchscreen, and FetchAid will automatically prompt the QR code scanner in WeChat to scan the code. Here, the user accidentally clicked the distraction button and is now in a commercial page. FetchAid guides the user to go back to the home page by first telling the user that they are at the wrong page, and then guide the user to tap the back button.
点击错误，请按照语音提示返回上一页，向左上移动，向左上缓慢移动，请点击按钮回到上一页。
After the QR code is scanned, the resultant page will contain the open compartment door's location,
柜门在您的左上方。
which will be read by FetchAid's OCR system to derive the world coordinates of the compartment door relative to the user's device. After the door is unlocked, other challenges entail. The door might be hard to find due to small opening or occlusion, and navigating to the open door might pose safety concerns because the user might be tripped or hit by the open door. The tool should also be aware of the 3D location of the open door to prevent the user from accidentally bumping into or closing the door. FetchAid first analytically derives the open door location based on text reading from the touchscreen. This method is much more reliable than vision-based methods, less prone to out-of-frame object detection errors common in handheld devices. Furthermore, the navigation tool needs to provide high-frequency feedback, which deems remote worker help impractical. And then it should guide the user to reach the door using real-time intuitive voice feedback. FetchAid uses voice and haptic feedback to guide the user to move to the target door location in closed-loop fashion. It repeatedly measures the user's current position and updates feedback. To minimize the confusion possibly caused by voice feedback, FetchAid guides user to move left or right first and then up or down. Once the user's distance to the target door is within a certain range, FetchAid tells the user to stop and reach for the door.
柜门在您的左上方，请向左移动，请向左移动，请向左移动，请向左移动，请向左移动，请向上移动，请向上移动，请向上缓慢移动，你已到达指定位置。
Before proceeding to user study, we want to evaluate each key technical component's performance under varied conditions to ensure the robustness and reliability of FetchAid, especially given that the task could be interacting with kiosk-like machines in outdoor environment. We validated that the training with data augmentation technique makes the CV algorithm and OCR detection component more robust across different angles and distances. We tested the AR identification module on 2 parcel lockers in 30 locations for each cabinet. It shows that the module was successfully guiding users to the target component with an average error margin within safe range. We conducted a user study, finally, to evaluate the impact of FetchAid on enabling BOV users to fetch packages from typically inaccessible parcel lockers. And we decided to leverage mixed method approach, meaning that we will be collecting quantitative data and analyze the success rate, completion time. We will also focus on getting qualitative insights from our users in terms of task load, effort, and frustration. So we use purposive and snowball sampling methods that eventually led us to successfully recruit 12 BOV participants with varying conditions of visual impairment. And for the user study, we provided our users with an iPhone 12 Pro Max running iOS 16 beta with FetchAid pre-installed, and we ran the experiment on 5 different actively used Hivebox parcel lockers with varying sizes and in different locations. We divided the user evaluation into 2 tasks. First one is touchscreen interaction, and the second one is open door search. The study design ensured randomness and fairness by varying touchscreen installation heights and UI designs and keeping consistent distance for trial pairs. We utilized a pair testing approach with 2 conditions. First one is baseline, the other one is experimental, meaning that completing the task with FetchAid. We applied a within subjects design, counterbalancing the order of conditions, have the participants start without FetchAid. Each task required participants to complete 4 trials, each trial with a 60-second time limit, which corresponds with the real-world timeout mechanism of parcel lockers. On the day of data collection, upon arrival, participants were first introduced to the experiments and asked to sign a consent form. They were then shown how parcel locker interfaces generally work if they're not familiar with it, and how you can use FetchAid to aid the process. In conducting the tasks, the sessions we recorded, after completing the task, participants rated their experience using a questionnaire adapted from NASA TLX, and they were also invited to participate in the semi-structured interviews, which is short, about 10 minutes exit interview for some in-depth qualitative insights. So each participant study session lasted about 30 minutes, with compensation provided according to local standards. Because of our study design, our data analysis contains 3 parts. The first one is to analyze the task data. We conducted the paired t-tests to compare success rates and completion times between baselines and experimental trials. And for TLX questionnaire, we analyzed the ordinal rating data with Wilcoxon sign rank tests to assess participants' subjective evaluation on task load, including mental, physical, and temporal demands, performance, effort, and frustration. Finally, we transcribed all post-study interviews. Initial analysis categorized responses relevant to task components, followed by thematic coding to uncover deeper insights into user experience. Comparing the task completion data of 2 conditions in experimental user study, we found that FetchAid significantly improved success rates in both tasks. It also significantly shortens completion time for open door search task. Users attributed such success in their performance to the intuitive voice feedback and also the error recovery support FetchAid provides. In users' subjective evaluation of the task load, they rated lower mental demand, physical and temporal demand, and they all agree that it leads to less frustration, better performance, and requires less effort with the help of FetchAid. FetchAid is a tailored smartphone application for BLV users to interact with parcel lockers via intuitive voice feedback. It is distinct from general vision detection apps in that it offers specific support for dynamic touchscreen interaction and locker access. Our findings from the qualitative insights tell us BLV users value the mechanism of error recovery support very much, and they think that is a key boost to their confidence in interaction with external machines. This might inform future designs for supportive technology for BLV population. And we do acknowledge the limitation of simulated scenarios in replicating real-world cues like door sounds in user study, but this might underscore the system's effectiveness despite these challenges. Finally, the real-world situations of parcel lockers is always messy. Many of them are actually located in outdoor noisy environments, which is exactly why sometimes environmental cues fail to provide our BLV users a general sense of where the open door is located at. And this led us to actually come up with the design consideration of providing the AI open door support. While the implementation of FetchAid was done with Hivebox, the most popular parcel locker in China, its principles could easily apply to other parcel lockers because the underlying logic is basically the same. It can also support potential user interface updates. It also has the potential to be generalized to other machines. Here are some products that would require touchscreen interaction and navigation needs we found are currently employed in China. In many other tech-oriented nation-states, with the rise of Ubicom, large system replacing human-human interaction with human-computer interaction or human-machine interaction pose challenge, especially in accessibility for BLV groups. And the solution provided by our system is a good effort in trying to hack the technocentric design. Finally, FetchAid aims to complement existing navigation aids for BLV users, which was well studied in previous literature such as Navcog, so that the system offered potential for an end-to-end navigation solution from broader integration, from home to the parcel. We also have plans to open source the code for community development and enhancements. FetchAid faces issues in low-light conditions and when users move very rapidly. In order to tackle this in the future, we should integrate low-light image enhancement techniques in our object detection model and a hybrid ML-based plane detector during AR navigation. Another next step is to address extreme failure. So we plan to develop an error recovery mechanism for unexpected scenarios like dock closures to guide users back on track. Observations suggest that there's a need for adaptive voice feedback to match users' evolving requirements and preferences for instructions. In our user studies, users show different levels of patience for voice guidance. Some want them to be faster, some want them to be slower. So this is another important consideration we should integrate in terms of personalization. Another aspect to consider in personalization is adjust the instruction frequency and feedback design to cater users with varying levels of residual vision. That being said, the design should be improved over time if we employ a longitudinal study plan so that we can get more in-depth long-term understanding of how BLV users engage with parcel lockers in the tool over time and if the patterns should adapt to their learning. Finally, the operating system of FetchAid. We developed FetchAid on iOS and conducted user study with a smartphone on iOS. Even though some participants, they use Android smartphone, our findings didn't show significant difference in the effectiveness of FetchAid, meaning that FetchAid is usable across different smartphone operating system habit. So the plan is to open source the code for broader accessibility, including development for Android devices. To conclude our research, FetchAid is a standalone smartphone app designed to help BLV users efficiently use parcel lockers with intuitive real-time voice feedback. Evaluation with real BLV users showed an increase of 30% in touchscreen interaction success rate and an 11% increase in success rate for open compartment door searches. In general, participants experienced reduced frustration and effort. They attribute improvements to FetchAid's real-time voice feedback and error recovery support. This work represents a development HCI for making interface interactions more accessible for BLV users. FetchAid marks a significant advancement in creating cost-effective third-party assistive tools that don't require additional hardware. It also enhances touchscreen operation, error recovery, and object localization with safety guideline features. Finally, this system utilizes cost-effective smartphones' neural network and AR capabilities to improve the usability of modern appliances and machines for the BLV community, which holds potential to address more accessibility issues and gaps in the age of ubiquitous computing.